Hello and welcome to this edition of Using R. And in this edition, over the next roughly half an hour, as we were discussing, we're going to learn how we can perform hypothesis testing in R when we have got continuous variables. So, let me give you a little bit of a context to this. And we will be exploring as to what do we do, in other words, the preamble to hypothesis testing with continuous variables. But it becomes really important that we should have a clear understanding as to why that is important, and particularly in R, as you know, it is rather easy to set up data analysis. But more importantly, once you know the theory and understanding of hypothesis testing and the deal with continuous variables, then it becomes very easy and intuitive for anyone to set up hypothesis testing in R. And so that's something that we're going to learn today. Part of it will be about learning about hypothesis testing, and certainly afterwards we'll see how we can use this. So let me introduce myself first, and then we continue doing this. As you know, this set of lectures are being produced for the e-Pathshala part of Indian government, and my name is Arindam Basu. I'm at the University of Canterbury in New Zealand, and we'll continue doing this. So the next thing is to talk a little bit about the learning objectives of these sets of slide decks. So the way we are going to learn here is I'm going to talk to you a little bit about the hypothesis testing world, and then we'll actually show you with a real life data. So we'll read a data set, and then we'll do two kinds of tests for continuous variables. One in which we're going to read two continuous variables, and we're going to test how we can run some of these tests, and what are some of the variations or variables or variability around those tests that we must know, and on the variations of the themes, for instance. And you'll see for yourself how these things work well. And then we'll have continuous with continuous and continuous with a categorical variable. We'll see how things go from there. And then we'll finally summarize the most important, perhaps, key learning points in this lesson. So to continue further with what are we going to cover, what are the objectives of this tutorial or lesson? First of all, we're going to learn some data from R. And if you are planning to set up data analysis on your own without much introduction to, say, formal statistics at all, I hope you will still pick up some of the very basic things. For some of you, it may be a little bit slow because you may be already familiar with the theory of hypothesis testing and everything else. But those of you who are not, you may find the following few slides to be quite useful. So I have I've done some of these things. So that's the reason why I have provided you some very, very basic, almost kind of a magnetic, very short, some absolutely zero-level basic idea about what does the word hypothesis testing at all mean. And then we'll run a little bit about introductions to how in real life somebody who wants to go about doing research work, like observing the world and then theorizing, wants to make some things work, two things. And then we'll get cut to the chase, and we'll talk about the nitty-gritty of testing with t-tests and analysis of variance, which is ANOVA. I must mention here that a formal, more kind of contextual, R-based introduction to the analysis of variance, particularly one-way analysis of variance and two-way analysis of variance, the maneuvers and everything else, I have already discussed using R in these tutorial sets. If you have not had a chance to take a look at them, you should look at them because they contain in much more details about the more nitty-gritty of what we can do in terms of using R for doing this. This is more or less an introduction as to what is quite possible and what people do when they work with R. So here is the deal. We will show you some basic ideas about hypothesis testing, then we're going to read some data sets, then we'll run a few tests, and then we're going to wrap up things. Okay. So without much ado, let's get started and let's talk a little bit about some very basic things about hypothesis testing and the cycle of doing research and leading up to the point where we start our data analysis. Now, it's probably better that I talk to you about the sequence of our testing, but I thought that I should introduce some very basic notions about testing our hypothesis. So the first thing that I think we should get some clarity around in our heads is this notion of hypothesis. Hypothesis essentially is a Latin word, and it is a compound word which has got two parts to it. The first four characters, hypo, tells you that it's beneath something. So it kind of, it's not, it sits under something. So something else must be sitting on the top of this, right? So that something which sits on the top of it is a thesis. And a thesis basically is a theory or kind of a thing that we, a theory or a way of looking at the world. And from there, we derive a statement about the state of the world. So, without a concrete example, it's still very woolly or wishy-washy. So maybe I should give you an example. Perhaps you are interested to find out whether there is any reason to believe that, cigarette smoking, if people were to smoke cigarettes for a longer term, they would end up with heart disease. That is your theory. And the hypothesis then that would flow from there is this, that people who smoke more cigarettes are more likely to develop heart disease. People who do not smoke cigarettes are less likely to develop heart disease. From here, from a hypothesis testing perspective, you can draw two kinds of statements, and both of them would be termed or referred to as hypothesis. The first statement of a hypothesis that you can draw is this, that compared with people who are non-smokers, smokers are going to get higher rates of heart disease. And this is known as the alternative hypothesis because this is a situation that you're challenging. Okay? Or let's say that the other condition is this, that the rates of heart disease amongst smokers and non-smokers will be very similar, if not identical. So it does come that smoking has got no association with heart disease whatsoever. And that kind of a statement would be referred to as a null hypothesis. Now, in the real world, you could argue that the null hypothesis could have a probability that it could be wrong or it could be right. We just don't know that. Remember, this is still in the realm or domain of hypothesis testing. So you will be centering your theory or your philosophy of doing all your statistical work or all your data analysis on null hypothesis. And why this is so? Because null hypothesis essentially is a situation where you take a position of equanimity, or it's kind of a position of equipoise. You could you could say that things are very similar, irrespective of the irrespective of what I think or whatever specific issues that I want to work on. And therefore, there are two types of hypothesis: the null and the alternative hypothesis. The alternative hypothesis is your new findings. And you could argue that the null hypothesis could both be false or true. I mean, yes, you make a statement of null hypothesis, but we just do not know if the null hypothesis is the correct thing in the world, or we do not know if the null hypothesis is the wrong thing to say. And accordingly, when you conduct your studies in which you obtain certain tests and then you obtain some results from your test, on the basis of those results, you may say that, okay, I am going to reject the null hypothesis. Or you find that the results of the tests are such that you are not in a position to reject the null hypothesis. Either way, you got two options. What I have done here is I have put together a 2 by 2 table. In that 2 by 2 table, I have pitted the possibility or the probability that the null hypothesis is true or the null hypothesis is false in the columns, and in the rows I have put together the possibilities that I am going to reject the null hypothesis on the basis of my test results, or I will fail to reject the null hypothesis on the basis of my test results. Then, on that basis, I have put together 4 cells. In the top left-hand cell, I have considered the fact that I can end up in my test results and in my decision making a situation that I have decided to reject the null hypothesis and claim that the null hypothesis is false. But in reality, the null hypothesis was actually a true reflection of the reality. When I did that, if I were to do this, I would commit an error. And this error is a rather serious error because my intention is to establish a new truth, but in establishment of this new truth, I have committed an error which I should not have. So my test is probably not very sensitive. So how low can I go? There is no real consensus on this, but it is a convention that I would probably go as low as 5 out of 100, or maybe accepted probability of 5%. And this error is known as type 1 error. I can make another error, and I have noted this in the lower right quadrant, and that is, in my tests, I have failed to reject the null hypothesis, but actually the null hypothesis is not correct. Again, I have committed an error, and this error is known as type 2 error. In a subsequent tutorial, we will revisit these notions again, and particularly during the sample size and power calculation, and therefore I'm not going to make a big deal of it right now. So focus on your type 1 error, which is known as the alpha error or a 5% error. This is important because this is what is known as under the condition of the null. So the next thing that I'd like to really focus here is the is a whole process of our testing and the sequence of our testing, and where does it sit in the theory of research. So let's take a look at that before we move on to using R for these calculations. In a sequence of our testing, we always start with a theory. So no matter who you are or what you want to do, whether you are a statistician, a non-statistician, but a domain expert who wants to actually study certain things, it is very important that we do our research to explain our world or describe a certain world phenomenon, and then would like to test it with what is accepted. So we start with a theory that kind of explains the nature of our world as best as it can. And a theory, which is the thesis, would lead to certain below propositions, which we call as hypotheses. We have already learned that there are a couple of ways in which we can state these hypotheses, one of which is known as the null hypothesis, the other is known as the alternative hypothesis. We have also learned that for both null and the alternative hypothesis, we can set up boundary conditions where our test will either conflict or will agree with how we can reject the null hypothesis. So the crux of our research is centered around null hypothesis, and we either reject or we fail to reject the null hypothesis. Based on this basic information which we set up in the beginning of our study, we go out and we collect samples of our data, and then we come back and run our analysis. There are a number of different ways in which we can run the analysis, and if our outcome variables are continuous and our explanatory variables are continuous, then we conduct tests such as t-tests to run them. If our outcome variable is continuous and our explanatory variable is a categorical variable, then we run t-tests, or depending on the number of levels, we can run ANOVA. Therefore, in this series of our tutorials, we're going to focus on either t-tests or ANOVA and explain what are the different ways in which we can do this. So let me start with some sequence of what we're going to show you in these series of codes. All of these are given to you in the form of brief R codes that you can review and practice for yourself. And therefore here we start with a description of the data that we have taken in, and then we are going to show you a few t-tests. We're going to show you the ANOVA, and we're going to just end it here because this is where we are going to be working most of the time. Okay. So in the next slide, I'm going to show you what data have we got. As you can see here, there are two data sets that we will be using in this set of tutorials. The first data set is a data set which is known as cars, and it has got only two variables, the speed and a distance that a car will go. We can obviously in future will show you that we can create some artificial conditions to show and suit certain things that we will be doing here. So that's one set of data set that is already contained within a within the cars data set, which is an inbuilt data set that comes with a standard R installation. The second one is one in which we use a package called the foreign package, and we are reading the foreign package, or the contents of the foreign package. And here it is like Like this is an SPSS data set, some file name .sav, and we are reading that by exporting that to a data frame. So we are reading that one, and this is known as a SciBike dataset, which is our very popular dataset that we have been using in these demonstrations of the last few cycles. And in here, we are actually noting the passing distance, distance from the curb, the different kinds of vehicles that are parked on a curb in a particular city, etc., etc. So we're going to use these two data sets. Some of these are continuous variables, some of these are categorical variables. You know which variables are continuous, which variables are categorical, and how to identify them. You can very easily type of, apply that particular function to the string of variables that are contained within the data set, and then you can find out what kind of variables they are. If they're continuous variables, then you know that they're continuous. If they are categorical variables, then you know that they're categorical variables. And then we're going to use this. In a second thing, next we're going to learn how we can use what is known as an independent samples t-test. In an independent sample two-group t-test, what we are going to do here is that we are going to use an outcome variable which is continuous, and we're going to use an explanatory variable, or a variable whose differences we are examining, and we are going to assume that this variable is a categorical variable. So this categorical variable will have two groups. In our example, we are going to take a look at the fact that in our data set on SciBike, that is psychology of the bikers with respect to how they were going to pass vehicles or how they were going to ride their bicycles in a big city, we are going to assume that some of them were wearing helmets and others were not wearing helmets. So here, helmet wearing is a safety procedure that some bikers were doing, others were not doing, and this is happening in a city where wearing a helmet is not mandatory. And we are also going to assume, or we are going to assume that people who were wearing a bicycle helmet would be justified to pass by the cars at shorter or lower distances than those who are not wearing helmets, because that's kind of if you wear a helmet, then you can afford to do that. So that's kind of a statement that we would like to make here. So a theory would be this, that people who are helmet wearers are more expert bikers, or they know they can afford to pass at closer distances than the other ones. A thing which is very important to note here is this, that there are different groups of bikers. People who are wearing helmets are different from people who are not wearing helmets. Not the same people. It is not like an experiment where we get some data from bikers who are wearing helmets, then we give them helmets to wear, and then we take the same data. This is not that kind of a study. Here, we are having two different groups of people who are independent of each other, who would either expected to wear a helmet or not expected to wear a helmet. And this is why the particular test that we are going to do is known as independent samples t-test. This is something that you should be aware of. In your real life, when you are conducting a study where your outcome variable is a continuous variable and your exposure variable is a categorical variable with two categories, and you are interested to run a t-test, always ask yourself that these two categories that you're using, for example, in this case, helmet wearing as wearing or non-wearing, whether these two categories represent essentially two different groups of people or not. That's the first decision that you should make. When you know that they come from two different classes of people, you should be applying an independent t-test. And a reason why this is very important is the simplicity of the R code. Take a look at this. What we have decided to do was that we decided to create an object which is known as toGroup_t, which is just a name of an object that I created. It has got no inherent meaning. You could do something else. But in it we stored the result of the t-test, and we say that it is t.test, just that, nothing else. It's just t.test, and then we have said that we have given the name of the outcome variable, which is the passing distance here, and then we put a mark like the tilde mark, and then we put the name of the variable of the exposure variable. Here it's helmet, which is a categorical variable, and we just left it at that, because R assumes, if you do not supply any other parameters, that it's going to be an independent samples t-test. However, sometimes you would really like to specify that this is an independent samples t-test. An independent samples t-test is also often referred to as a paired t-test. So you should write paired and then put a T mark to it, which means that it is true that you're, or put an F mark to it, stating that it is false. So you're not running a paired t-test, you're running an unpaired t-test. And then all you need to do then is to ask R to put out the outputs, and R gives you the outputs. It first puts out the data, then it shows you the t-statistic, then the degrees of freedom, and a p-value. You can see here that the p-value is very high. What does this p-value indicate to you? This p-value tells you that the data that you had obtained, in other words, the averages of the passing distance for the bikers who were wearing helmets and the bikers who were not wearing helmets, that difference would be, that difference would be the, the true difference would be zero. In other words, there would not be any difference at all. The true difference would be zero if that null hypothesis were to be correct. Under the conditions of the null, what is the probability of getting the findings that we are getting? So if the true difference were zero, if the null were to be true under conditions of the null, the probability of the difference that we are getting here in this particular data set is likely to be 0.00000 whatever, 8 places to the decimal. Extremely low, very low. Not only this, it also gives you a 95% confidence interval that the true difference is not equal to zero. So what it would say is this, that whatever may be the difference, and you can see that there is a mean in the group 0, which means the mean of people who were not wearing helmets is 1.35 meters, and a mean for people who were wearing the helmet was something like 1.27 meters. Therefore, the difference is about 0.08, and you can see that the 95% confidence interval is something like 0.05 to 0.12. This is an example where you see that there is one outcome variable which is continuous, and one outcome variable that is, and one other explanatory variable that is categorical. We'll do one more thing, and this time we're going to show you that we're going to have two variables that are kind of independent samples that we will test. Okay, and this is quite interesting. So we next show you that two independent samples, but this time we are using the cars dataset. Let us say that we have got two different varieties of cars. Maybe one group of cars are like SUVs, which are like really big vehicles, and the other ones are really small vehicles. And so these are two different samples of these two different cars. So they are independent samples. And we are just going to make a test whether there is any difference in the distance that they're going to cover with the same amount of petrol put into them. you would argue that you know that they'd be different, and um, or you could argue that no, um, they're not going to be really different from each other. So this is again a situation where you can see that yes, they are different, and you can see that the smaller cars, like the ones that had um, for you know for which that the variables was dist, you see that they go far longer miles, the mean of y compared with the mean of x, and you can see that there is a that there is the difference is almost like 36 miles or 36 kilometers difference, and you can see that, or minus 36 in this case, and the difference is the 95% confidence interval is going to range between minus 33.8 to minus 18.9. And the other thing that you get to see is this, that the p-value is very, very low. So 3 and then 10 to the power of minus 9. Huge difference. So this is a very simple way in which you can set up independent samples, t-tests, paired equals false, and you could get the t-test. Very simple syntax, it's just t-test. And if you do not mention as paired, the paired is usually given that it's a false one. Okay. The next one, we're going to run a paired t-test, and take a look at this. Next, in the same situation, let's say we have done what is called an intervention, so that for the same cars we have just did some some mumbo jumbo, I don't know what it is, and then we decided to test the two distances of the same group of cars. And you can see now this time, we made some technological changes so that with some cars, like the ACVs, say for example, they have got a higher, they're going to go longer distance. So do they go longer distance? That's what we want to find out, and or whether we go no. And you see that yes, they do go longer distance. Once again, you reject the null. You can see that there's a very, very small p-values, and we took like 50 cars and we did this. And then you have got like the true difference in means is less than 0, and then we say that the mean of differences is minus 21.9. That's a paired t-test, because the same group of cars given an intervention, and we have taken two different values for the distances that go on the petrol mileage, and we see that the second one goes farther distance. Therefore, there is a negative when we subtract them, and you get a value. The last one that I'm going to show you is that instead of using only two categories of a t-test, we've got more than two categories. So we're going to run an ANOVA. And here we're going to say, the passing distance by the vehicle type. And you can see that when we do this, maybe if the vehicle is big, then you don't your passing distance is going to be farther out. If the vehicle is a small size vehicle, then you may have a closer passing distance. That's sort of an idea. And you can see once more, the test to do is ANOVA, and it's a very, very simple syntax. In R, we just use only one function called AOV. Then we give the passing distance, which is the outcome variable. Use a tilde mark. We give the explanatory variable or the exposure variable, as the case may be, and then we put out the summary of this. Very simple syntax, and you can interpret that there is a significant difference. You could also take a look at the residuals, the sum of squares, and the degrees of freedom. As we have already done ANOVA before and earlier, I'm not going to repeat the more nitty-gritty and details here. I encourage you to go and review those bits. So now we have learned how to interpret and compare two continuous variables. We have learned about the t-tests, and we have learned about the analysis of variance. Thank you very much for paying attention.